All right, welcome to seminar. We're going to go ahead and get started. We're going to have a prayer by Zach first, and then we'll go through some announcements.
Our Heavenly Father, we're grateful to be here in seminar, and we're grateful for this wonderful last few weeks we had before finals, and we pray that that would bless us, that we may retain the information that we continue to learn, and that will bless us in our studying. We pray that as we listen to our speaker today, that we'll be able to greater understand what that would have us do in our civil engineering careers. We pray that we can be respectful and that we can learn much from him. And we pray that we can finish this year out well. And we say this in the name of Jesus Christ. Amen.
Okay. Just a few things coming up to wrap up the semester. Seniors, you need your leadership points still. Go ahead and contact us because you probably want to get an A in seminar. And we're going to do this stuff for Santa for anyone who still needs service points. So, what is this? And this is also on the blog, so if you don't catch all of it, you can find it there. Rocky Mountain Conference, it's about that time to register. So anyone planning on going, it's really fun experience. You get exposed to a few things that, well, at least for me, has really solidified my choice in civil engineering. It's made it more bearable, the school. They're showing the Dream Big movie next Wednesday, and that's free, right? Yeah, so it's free. It's supposed to be really cool, so I encourage everyone to go to that. Having a closing social, so let's party. Also, elections are coming up. It's time to nominate your friends, or if you think would do a good job, or if you just want to do it, you can nominate yourself. There is a Google form that you can fill out on blog or on the Facebook page. And one last Habitat for Humanity. That has been a really good experience for everyone that's gone, from my understanding. So if you need service, try that out. Okay. So Mr. Hiram Alba, as a senior principal and senior engineer at GeoStrata. GeoStrata is a geotechnical engineering, geologic, and environmental consulting firm that also provides material testing and special inspection services in Utah and the surrounding states. Hiram has been involved in geotechnical and geological engineering projects since 1985 and has been a practicing professional geotechnical engineer since 2000. Received his BS in geological engineering from the U in 1985 and is the founding principal of GeoStrata, which has been a geotechnical consulting firm since 1998. Mr. Alba has been involved in many complex geotechnical engineering projects, which include highways, bridges, dams, landslides, assessing debris flow hazards, fault studies, and rock fall hazards. Geostrata specializes in 4 specific technical areas: geotechnical engineering, engineering geology, environmental geology, and materials testing and inspection work. It's a local company in Bluffdale with 35 employees. Our work is performed throughout the Intermountain West. Our clients range from large construction companies, irrigation companies, builders, cities, and other government entities and private development. Mr. Alba's worked at those places that you can see up there. And despite having graduated from the U, is an avid BYU fan. He's licensed professional engineer in 7 states: Utah, Idaho, Wyoming, Colorado, Nevada, and North Dakota. And he is a licensed professional geologist in Utah. So let's welcome Hiram Alba.
Well, I'm excited to be here. I normally have kind of a tough time coming into Utah County. They kind of set a border watch for me. Number 1, I'm a Democrat. Number 2, I'm a graduate from the U. So they try and keep us individuals out as much as they can. I actually emceed a program, an awards program for the American Council of Engineering Companies. I don't know how many of you know what the American Council of Engineering Companies is. It's an organization similar to ASCE, but you can swap this over to the presentation. But what they are more involved with is the business of consulting engineering. So and for those of you that are not aware, my wife kind of generally dresses me. I don't dress, she buys my clothes, and I was wearing a sweater that night similar to this one. One of my employees came up to me and said, "What are you trying to pull off the Mr. Rogers look?" And I said, my only comment back to him was, "Your review is coming up quickly, so I wouldn't get too angst on commenting on your boss's attire." Geostrata. I started Geostrata as an engineering company in 1998. We've been in business since then. We've got about 35 employees. We kind of generally specialize in 4 specific areas. Although there's more than 4 listed, but we specialize in geotechnical engineering, geological engineering, environmental engineering, and testing and inspection work. There was a reason I started Geostrata, and I'll go to this next slide, and hopefully it shows it. I like working on dams. I had worked for other foundation engineering consulting firms, and I like doing foundations. That's a major part of the business that we do. But I really like to focus on dams. And the reason I do is from a geotechnical engineering perspective. When you're looking at foundations, normally you do a study, you're done and you're out. You don't normally see anything that's built after the fact. But in dams, you stay involved with the project from the beginning to the very end. This is actually a map that shows the various dams that I've worked on throughout the Intermountain West. Up into Idaho. I got to back up here, sorry. We're currently working on a dam over in Colorado. I've worked on several in St. George, one in Idaho. The one in Idaho was on the Bear River. It was a small diversion dam. It was an RCC dam, roller compacted concrete. It was a lot of fun. It was a great project. I've worked on 2 roller compacted concrete dams. That one in Last Chance up in Idaho, and one in Centerville. It's a debris basin dam that's about 70 feet high. So what I wanted to do mostly was kind of talk about various projects, but I'm here to kind of answer any questions if you're interested in how to run a business, why I'm in the business, things that are challenging, and hopefully as we kind of go, feel free to kind of raise your hand, ask questions on any of this. So we're going to talk about the very first project I worked on when I graduated from the U. It was on the Smith and Morehouse Dam. How many of you have been to Smith and Morehouse? Do you know where it's at? It's up by Oakley, Idaho. It was the rebuilt dam. They removed the older dam. The older dam had a capacity of about 1,000 acre-feet. This new dam was 3 times higher than the older dam, and it increased its capacity from 1,000 up to 8,000 acre feet. I worked on that dam for 3 years. It's a beautiful valley. It's a great place to work. The commute was kind of stinky. I drove up every day, worked 12, 14 hours, and then drove back to Salt Lake every day. But it's up in the high Uintas. It's 70 feet high. Let me go to it. And it's a high hazard dam. Now, I worked for the state of Utah's dam safety section. Palmer Wilding was building the Smith Morehouse Dam. After that, I went to work for dam safety. Dam safety classifies dams based on high, moderate, and low, and they classify them based on flood inundation maps. So this is the flood inundation map for Smith and Morehouse Dam. So what they do is they say, all right, if the dam experiences a rainy day break, it fails, an instantaneous failure, which doesn't really happen, but that's how they look at it. What type of flooding is going to occur downstream? If it has a potential to kill anyone, then they call it a high hazard dam. If it has a potential to damage others' property, but not necessarily kill someone, then it's a moderate hazard dam. If it has only the potential to damage your own property and not affect too many other things, then it's a low hazard dam. And the work that you do on these dams becomes more and more intensive based on the hazard rating. So Smith and Morehouse is a high hazard dam. As you can see, as the flood comes down, it'll pretty much take out quite a bit of Oakley before it works its way down to Rockport. All right, here's a picture of the spillway. They actually had a video tied to this, and I wouldn't recommend this, but this spillway, they were tubing down the spillway. The problem with that is down at the bottom of the structure, we designed energy dissipation structures. So big concrete blocks that sit at the bottom of this thing. So it was really kind of interesting. They seemed to, the water was deep enough to where they weren't affected by these blocks. But the reason I wanted to show this slide is because of the concrete bridge up here at the top. You can barely see the outline here. The walls on the spillway are about 35 to 40 feet high. I was there during construction, and that's a pre-stressed concrete bridge that was placed across the spillway walls. So they built the spillway first, and then they brought in all of the earth adjacent to those concrete walls. Well, what happens is concrete flexes and it moves, especially when you're compacting 60 feet of soil out here adjacent to it. So these spillway concrete walls started out vertically, and as the dam was constructed, started to kind of angle in towards the pre-stressed concrete bridge. And eventually, over time, the concrete bridge blew out the sidewalls on the spillway. So it was really kind of interesting. It was an interesting problem that hadn't really been foreseen. I'm not a structural engineer, so you can't blame me for that. The soils have worked out well. The dam has been a great project. I love going up there to see it. So that's the Smith and Morehouse Dam. Next project I wanted to show was Deseret G&T, which is the Bonanza Power Plant. This is an aerial view of the Bonanza Power Plant. I was hired directly by Deseret G&T after I worked with the state as a geotechnical engineer. I was kind of an odd duck. You know, all of the other engineers at Deseret G&T were electrical, mechanical, civil. I was the only geotechnical engineer, and there's a reason why I was hired as a geotechnical engineer here. So the site kind of borders around this area is about 1,000 acres. This is the main power block right in here. These are the wastewater ponds, and this is the raw water pond. They pump water from the Green River 30 miles and dump it into this raw water reservoir. The design on the project was done by not a geotechnical engineering firm. It's a civil design firm out of Kansas City. It's a very reputable firm, very big firm, probably about 600-800 employees. Do a lot of international work. They build power plants all over the place. In this instance, they decided that they were going to do their geotech on this particular site. Well, what's interesting is environments are quite a bit different from Kansas to Utah. They did a study. They did find and identify hydrocollapsible soils at the site. But in general, they underestimated the impact that this facility would have on those hydrocollapsible soils. Now, is everybody familiar with hydrocollapsible soils? Do you know what they are? In their dry state, they are very strong and they can support just about anything. But when you introduce water to them, they collapse. Thus the term hydrocollapsible. Well, So this whole area has hydrocollapsible soils throughout. They did recognize it, they did test for them, so all of the power block was built on piles. And they extend down to bedrock or nearly bedrock, and that's supposed to be the main power block. This is a couple of pictures of the main power block, just so you can see how big the structure is. It's a 500 megawatt plant, it's pretty big. I'm gonna back up a little bit, back to this. So we've got hydrocollapsible soils everywhere. The gradient is from the top, from the north to the south. Where do they put all of their wastewater retaining ponds? To the north. What happens with ponds if they're not lined? They leak, and these leak. So the main power block was fine, but what we found was we had RO tanks that were probably 30 to 40 feet high that had tipped almost, not quite like the Leaning Tower of Pisa, but at least 18 inches out of verticality. The transformers were regularly moving to where every year they had to add additional leads onto these things because the electrical wires were too taut after the settlement had occurred. So all kinds of facility problems that were going on in this. That's why they hired a geotechnical engineer. The owner wasn't happy with it. He ended up suing the design engineer. I didn't give you their name for a reason. They ended up settling for $20 million, which is a pretty big chunk of change, and that's why I got hired. That's what funded my position. My responsibilities out here during that time was just to try and figure out how to control the groundwater. Model it, find out where it was going, try and minimize the water seepage out of these areas towards the main power block and all of the other facilities. It was a great job. I really enjoyed it. We worked on some great projects. We worked on some dewatering well systems. We worked on a dewatering trench. We did some designs on things. And it was a lot of fun. We had a really good time. The only reason I ever changed jobs, to be honest with you, was because my job was based in Salt Lake. They said, hey, we're doing away with your position here. If you want it, you're going to have to move to Vernal. No offense to Vernal, I really like Vernal, but my wife's like, I'm not going to Vernal. So I ended up finding another job. I ended up working for Kleinfelder down in St. George. So that's the story behind Deseret G&T. This one is another reservoir that I worked on. It's also a moderate hazard, a high hazard dam. It's actually right at the point of the mountain. I don't know how many of you have seen this. It's kind of tough to see. This is I-15 here. You've probably seen everybody kind of hang gliding off of this point right here. This particular dam was designed by another firm, again in Colorado. During construction, they did some value engineering on the structure. It was meant to be a concrete line, about a 20-acre reservoir. The water comes from the Provo Aqueduct, which comes out here through an 84-inch diameter pipe. It's a pretty big pipe, dumps into this thing. During construction, the contractor did some value engineering and found out that there was a little bit of a flaw in the structural design on the liner. And that is, the original designers didn't space their concrete cuts close enough. And they thought the cuts, for those of you that aren't familiar, they put concrete cuts on the concrete to kind of control cracking in the concrete, right? Well, they'd spaced them out too wide, so the contractor came to the owner and said, this structural design isn't going to work, you're going to have a lot of cracking in your liner, what do you want us to do about it? The contractor came to the owner and basically said, the additional cutting on this thing is going to be close to $500,000. Are you willing to pay for it? And the owner kind of backed away and said, no, we don't want to do that. We'll hire Dunn Geotech. Hire him. You want to come in and do this? So I got hired to do a redesign on the dam. Not the dam itself, but just the liner system. So we came up with a double lines HDPE liner. You can see the HDPE here and here on this side. It lined the entire reservoir. It is regulated by dam safety, so they came out and did inspections on the dam. I ended up becoming the engineer of record, which is a little bit disconcerting. Now, I don't know if you know what that term means, but the original designers were the engineer of record until I changed the design. Once I changed the design, I became the engineer of record, which means all of the liability, if this reservoir ever has a problem, gets transferred to me and my company. So, you know, we were pretty cautious about the things that we were doing, how we placed the liner, made sure that there was plenty of testing and things that went on. So, and it turned out really great. The owner ended up saving quite a bit of money. He didn't have to pay those additional costs in order to do all of the concrete cutting. So it turned out to be a really good project for us. Let's see, where am I at here? Oh, okay, moving on to another project. This is the North Jordan Canal failure in 2013. And those of you that are familiar with the Salt Lake Valley, there are a lot of canals that come from Utah Lake and the Jordan River that spread out across the valley, both on the east side and the west side, that carry irrigation water from the south end of the valley up to the north end. So in 2013, there was a canal failure right here in Murray. This is about the approximate location. We were contacted by the owner to come out and, number one, do a forensic study, what caused the failure of the canal, and then number two, design with the civil engineer how they were going to reconstruct this thing. What's really kind of interesting is, for those of you that aren't aware, my degree is in geological engineering. It's a little bit different than geotechnical engineering. It's a lot of geology and a lot of civil engineering. So I do take all of the courses in geotechnical engineering, but I take a lot more geology. That's why I'm licensed as both a geologist and a civil engineer. So here's a couple of pictures of the failure. This is the hole itself. It flooded out a neighborhood. It didn't kill anyone. Luckily, it didn't kill anyone. But it did flood out about 8 or 9 homes. It was a pretty significant chunk of the canal. You can see the water down in this area and kind of some of the damage that it did. The first thing that we did, and this is the first thing that we always tend to do within our group, we have a lot of geologists. I've got about 8 or 9 geologists that work for me, which is kind of an inordinate amount. But they do a lot of really good work. First thing we did was we looked at the geologic map. And what was interesting about the soils in this area, and this is a surficial geology map, is you see this little blue spit right here? It's called a sand spit. And this sand spit, all of this other material in here is Lake Bonneville deposits, which are interbedded clays generally, clays and silts, interbedded clays and silts. But this is a sand spit. So this is where the failure is at. Right near the failure, all of a sudden the soil changed from clays and silts into sands, which was kind of interesting. As we were looking at some of the photos on the failure, this is one of the sidewalls. Do you know what this is here? Yeah, it's a hole. Do you know what caused it? A rodent, a muskrat, a rat of some type. So some animal burrowed from the outside of the embankment, through the embankment, all the way into the end of the canal. Now, how many of you are familiar with piping failures? Do you know what a piping failure is? What's a piping failure? Can you tell me? Go ahead.
When water slowly makes its way through the dam and carries away more and more water until you get a big old hole.
Yeah. Yeah. Essentially what it does is the material doesn't have any cohesion in it. Let's go back to this map. All of this material in here has clays. The clays have cohesion. That cohesion tends to hold itself together. It doesn't pipe. But that sand that was present right there does pipe. It doesn't have any cohesion. So as that animal burrowed through this little embankment, it created this little area where the water could seep out, and over time it would just grow and grow and grow. So this wasn't necessarily the burrow that caused the failure. We think there was another burrow down further, and that's what caused the failure on the canal. So we ended up coming in, we ended up lining the canal. We put it in an RCP, basically a big pipe through this particular area, because those problem soils only existed right within a 200 to 300 foot area through that sand spit that was defined by the geologists when we were looking at this. So it worked out really well. Another great project. Let's go to the next one. I'm trying to think of this project. Where are we at? Oh, I think this is the Ogden Siphon. This is located right at the mouth of the Ogden Canyon. There's a pipeline that carries water. It's a 36-inch pipeline that carries water from Pineview Reservoir down the canyon and then crosses over the canyon and feeds all of the land down here for irrigation. So we were contacted by a structural engineer in California that was doing a seismic upgrade to this particular structure. And this is the structure. It's a 36-inch pipe. It sits above the canyon about 200 to 300 feet. My geologists and engineers were really nervous. We had to investigate both this abutment and this abutment over here. It's kind of a north and south abutment. They wanted to know during a seismic event, is this structure going to stay together? So we're not looking at the structural components of the structure itself. We're looking at the abutments. Are the abutments going to stay together? They were wanting to know that. This is a picture of one of the anchors. This is the guy cables that come in. This anchor is just basically a concrete hole. This was built in the 1930s. So they excavated a hole back into the bedrock about 30 feet, filled it with concrete, put some reinforcing in it, and then tied these anchors to their cables that were suspending this siphon. So we did some drilling. My geologist, in fact, one of my engineers to this day, I just make fun of him because he was so nervous about hanging off this cliff that he crawled all the way out to the edge and crawled all the way back. We had harnesses and everything for him just in case he slipped, it was going to catch him. But to this day, he thinks this is one of the worst events of his life. So we wanted to look at some of the geology. So we brought in ground-based LiDAR. We couldn't really climb up and down the face. My guys aren't good rappellers. They're not good ropes guys. So we ended up using ground-based LiDAR. We took a photo of this, kind of scanned the hillside of the cliff in about 3 or 4 different areas, and our geologists mapped the joint sets. So they came in and defined the prominent joint sets and the directions, their orientations, where they were going. And lo and behold, what we found out was that these particular anchors and their excavation paralleled a prominent joint set. Which means, here's your excavation going into the hillside, and you've got joints that parallel it coming out of the hillside. During a seismic event, we basically said, look, this thing has got a really high potential of popping right out of the ground. So a part of the remediation was we recommended that they actually drill new anchors and that these anchors be oriented almost perpendicular to the current orientation that they had. So it was kind of a structural challenge. You've now got anchors coming in opposite directions from the majority of the stresses that are being put onto this thing. So this was a lot of fun. It was a great project. We had a good time, other than my guy being a little scared. This is molybdenum treatment plant that we worked on for a mining company here in Utah. And I can't give you its name, but I'm sure you probably guess it. It was a great project. It was an $800 million facility. We ended up installing about 200 deep driven piles and 1,200 micro piles to about 30 to 40 feet to support the structure. They were pretty bad soils out here. The client, was really happy with the way things went. This is kind of some of the things. We had some unique problems that came up. He was putting in a substation out here, and the soils didn't provide enough resistivity for his grounding mat at his substation. So we had to actually find a source, another source of soil with a higher resistivity that he could mix into the native soils here so that they could build their grounding net and be safe with all of the electrical systems on the substation. What was really kind of sad about this was, from an engineering perspective, it's great because this facility is going to stand forever. And the reason I say that is right after they built this, they had a major landslide at this mine, and I'm sure some of you heard about it. And the molybdenum that they were going to mine was now buried under about 400 feet of soil. So they ended up mothballing the plant. They never used it. $800 million kind of just went down the drain. All right. Last project I wanted to talk about was the North Salt Lake landslide. And I don't know how many of you are familiar with this. This is another project that we were pretty heavily involved in. This is a landslide that occurred in a residential development in North Salt Lake. These are kind of the limits of the slide here. It only actually destroyed this one house and destroyed a tennis court over here. Well, it could have been quite a bit worse. This house is still standing, and in fact, the owner is fairly happy and comfortable that things aren't going to affect him. Again, from a geology perspective, the slide is a little bit curious in its orientation. When we did our studies, we found that the slide was not moving directly north, but it actually rotated around here and pushed it to the north and east. So these homeowners were kind of wondering, well, are our homes going to be okay? If you can see a color change from here to here, it goes from kind of a grayish color here into more of a reddish color here. Actually, what happens is there is a fault that travels through this area right in here. And that fault is right on the boundaries of this landslide. So on the west side of the fault, there's some fairly competent bedrock. On the east side are Lake Bonneville deposits that failed during the landslide. So this landslide, that's why it moved the way it did. It followed that failure plane, the fault plane, and kind of pushed it away from these residences and over towards the north and the east. So it was pretty interesting. It was an interesting project. We were actually working for North Salt Lake City at that particular time. We continue to work for them. So we originally were just doing reviews, but after a period of time after this happened, they didn't feel like there was anything that was being done, enough was being done, so they asked us to get involved in design on remediation for this thing. So we did after a couple of years. These are the borings that were placed out here. We kind of color-coded them by the different consultants. There were 4 or 5 different consulting groups that were involved with this. The only ones that we did are these 2 right in here, and then 1 down in here. The only reason we did this is these other consultants did some work that we felt was a little inadequate in defining what the landslide actually looked like, what the subsurface looked like. So we did our own borings through there. That kind of shows where the borings are at. This is our back-calculated slope stability modeling that we did. That's one of the ways that you use to define what your soil strengths are in here. We gathered some samples and we did some lab testing on these samples, but oftentimes this back-calculated modeling gives you a better indication of what the strength actually was when this failure occurred. The profile here, when you look at these different layers and things, is actually defined by our engineering geologists, not by the engineers. They understand the geology better, they understand the depositional environments, where things would lay, how they would lie, the angles that they should lie. So they're the ones that generally generate these models, and then the engineers come in and actually perform the modeling to find out, how stable it is. And on our back calculation, here's our factor safety here for those of you that aren't familiar with it. It's just slightly over 1. Anything less than 1 means there's going to be a failure. So we felt pretty comfortable. We were pretty close to defining what those soil strengths were in this. We also did post-stability landsliding. These blue knobs down here at the bottom actually represent a buttress that we had recommended they place in order to stabilize the slide. If you look up here again at the factor safety, generally on slope stabilities, you're looking for a factor safety of about 1.5. I don't know if you can read that number. Can you read it? 1.3, which means we can't get it stable enough to meet generally accepted standard of care. There are things that you can do, but they become extremely expensive, millions and millions of dollars in order to stabilize it. If you go back to this, it's not really impacting anything. This house has been demolished. There's a roadway here. So even if this thing were to fail and move, it's moving in this direction. It's not really going to impact too much. So that if the city felt comfortable in saying, okay, we're willing to accept a lower factor safety, let's just go with what you've done. So we did. Well, I should say partially. Our recommendation, this buttress design costs about $2 to $2.5 million. The city didn't cause the problem. We ended up writing a forensic report and kind of pointed the finger at some people. And they're right in the middle of a lawsuit now trying to figure out who's going to be paying for what. But because the city didn't cause the problem, they don't have the funds to build this buttress. So guess what's happening with the slide? It's continuing to move. We did some minor things. They gave us about $800,000 budget. We did some grading. We did some other things on the slide area to try and minimize its continued movement and its hazard. But we don't have the money to really build what we need to. So every year we get called by the city, hey, the slide's moving, and we're like, yeah, we told you it would. They're not happy, we're not happy, but that's kind of where it's at. All of the other engineering firms were involved. They were all involved in designing or aiding in helping us design this particular buttress. So that's the North Salt Lake landslide. And that's the end of my presentation. Are there any questions? I want to talk a little bit about my history. Both my parents are from Mexico. I'm actually a first-generation immigrant to the U.S. My parents were migrant workers, so I was a little too young. They used to travel up and down the coast, on the California coast, up to Oregon and Washington. And when I was growing up, we moved from Mexico here to the U.S. when I was about 4 years old. I grew up on Spanish and English, both languages. But my parents were great about education. They, in essence, when I worked out in the fields with them, they'd say, hey, do you like this job? And I'm like, no, I hate it. You know, we're doing farm work. Nothing against farmers, but I don't like this. And they said, well, if you want to keep doing this job, don't go to school. So they were really adamant about going to school. I am the 10th of 12 kids, so I'm way down on the lower end. I never had a lot of money, but what was great was I just followed my older brothers and sisters' examples. I've got an older brother that's a lawyer, that's an attorney, that's a retired federal judge, another brother that's got a PhD in education, another brother that's got a master's degree in psychology. So I am the least educated of all my brothers and sisters, which is okay. I'm okay with that. But they were a great example. I had no idea. I just thought, hey, you get out of high school, you go on a mission, you come home, and then you go to college. I thought that's what everybody did. I didn't know you had a choice, but I'm grateful that my parents didn't give me that choice. One of the big problems that I ran into from a consulting perspective was I graduated from the School of Mines, not from the College of Engineering. And the School of Mines at the U does not require you to take the FE when you graduate. So my first job out of school was working for a consultant, Palmer Wilding, up in Bountiful, and immediately noticed that if I was going to get anywhere, I was going to need to get a PE. So I didn't take my FE until 2 years out of school. And if I can give you some recommendations, don't wait. It is hard. When you're out of school for 2 years, you lose those study habits. You forget a lot of the things that you retain. How many of you have taken the FE, by the way? And how has it gone? Any challenges? Fine? Okay, now picture yourself taking it 2 years from now. That's the struggle I had. So I actually did not pass the FE the first time I took it. I needed a 70, I scored a 67. I was really upset. I was going to become a seminary teacher. I just said no. But I persisted. The next time I took it, I did fine. I took the PE 4 years later and studied my guts out. What is interesting about my degree is, and those of you that are familiar with the PE has questions just like the FE in all types of engineering. So structural engineering, transportation engineering, geotechnical engineering, groundwater, other things like that. Well, I'd never taken structures. I didn't have anything on structures. So when I got to the PE, I didn't study structures at all. I looked at those structural questions and said, well, I'm not doing that one, I'm not doing that one. So it's easy enough to pass if you focus on the areas that you have expertise in and kind of broaden yourself out a little bit into those areas that you don't. So I did some open channel flow. You know, I can do some open channel flow. And it was great. I passed the PE with a fairly high score. I felt really comfortable with it. So I'd encourage all of you to take the FE as soon as you can. The FE is important. Getting a PE, I think, is critical. And here's one of the reasons why. When I worked out at Bonanza Power Plant, I was one of only 2 engineers that had a PE. So here's an engineering department with about 15 engineers. And guess who got to stamp everything under the sun? Well, the 2 PEs, they're the only ones that are licensed, right? Well, I didn't. The other guy was a little better at structures and electrical than I was because I didn't know anything about it. So he ended up signing and stamping the majority of things. But I saw some engineering things that just were really inappropriate. When you get into industry, they will not require you to get a PE, but my boss really encouraged all of us to try and get a PE. It's important to have. It doesn't automatically make you all knowing and all knowledgeable, but it does help you with the things that you're doing. Okay, any questions? Yeah.
I had a question on that, the Salt Lake plant side.
Uh-huh.
Do they do, like, geological testing beforehand? Like, in that case, they had a hospital right up against the road.
Yeah.
Like, why wasn't that back up to it, or it's like?
It actually was. There was a study that was done in 2004 by a consultant. Now, let me back up to this. That particular area and that hillside was a reclaimed gravel pit. So they mined as much of the gravel and the sand that they could, and the only thing that was left were clays. You don't use clays in creating aggregate or materials for concrete and asphalt, right? So the mining company sloped it down to a 2-to-1 and left it there. In 2004, they did do a study. There was a consulting firm that did a study and recommended fairly significant, it was a cursory study, they didn't get into details on it, but they did identify the potential for landslides in that area and recommended that some deep borings and other things be done. They were just never done. Another consulting firm came in, was not familiar with it, did some things that they probably shouldn't have, didn't do enough in-depth studies, and kind of missed the problem that was there. So that's a good question. I mean, one of the first things that we do as engineers, as geotechnical engineers, when we get asked to get involved on a project, is what work has already been done, and can we see it? Because there's no reason to duplicate something that's been done, and you can often garner a lot of good information that will help you with your studies. Any others? Yeah.
So you mentioned that one of your jobs you were hired on to help basically clean out the bottom of the soil.
Yeah.
Do you ever have any problems with that happening?
With hydrocollapsible soils, that project continues to have some issues and problems, some settlement issues. Their groundwater recovery systems are still current and active. They recognize that if they let them go, the groundwater level is going to rise. The only way they can get away from that is either moving the ponds to the other side, which they can't do. That'd be millions of dollars, not just in new construction, but rerouting all of your piping systems to a new direction. So they continue to use these things now. They haven't had any major failures yet. So it's worked out really well. But hydrocollapsible soils are not unique to the vernal area. We have them here in Salt Lake. We have them in Saratoga Springs. We have them in Nephi. I don't know, years ago, those of you that used to travel I-15 going south, I don't know if you remember the bridge at Nephi. Do you remember that bridge? What happened is you had a bridge that was built on a deep foundation system, so it bypassed all of the hydrocollapsible soils. But the abutments leading up to the bridge were just soil embankments built on the hydrocollapsible soils. So over time, those settled, and what would happen is they'd have to, you'd in essence, create a little launch ramp on I-15. Whenever you hit that bridge, you hit that thing going 70 miles an hour and kind of fly 2-3 feet up in the air. So they were continually adding asphalt in order to try and smooth out that problem. So hydrocollapsible soils exist throughout all of the state and in a lot of the desert environments. Anything else? Anything about business? I tell people all of the time, the smartest thing I ever did was start my own business, and the dumbest thing I ever did was start my own business. It's tough.
What was the hardest thing when you started the business? How did you get capital and employees to start out?
No, I had two partners when I started originally in 1998. We each threw in whatever money we had. At that time, the only money I had was my retirement, which was $50,000. So I threw in $50,000. My partners each threw in, one threw in another $50,000, and then the third threw in $100,000. So he owned twice the company when we started. But it is tough. I mean, we recognized that we didn't have, and me especially, I moved from St. George up here to start the company, so I didn't have a lot of existing clients. So we paid ourselves about $10 an hour for the first 6 months that we worked. So it was a big sacrifice. It was big financially, it was hard on us. But we kind of caught steam in a real big hurry, and I like my ability to market. What I found is engineering is great, but I like golf even better than engineering. And clients like to golf. So I had a lot of fun. I enjoyed meeting people, talking to people, and to me, because we were good marketers, it made us successful. Anything else? Yeah.
It's not business, but I was just wondering how you generally reroute the water when you're constructing your dam.
Generally, what they'll do is they'll do a little diversion dam. So the upstream of where you're building your main dam, they'll block off the river, and they'll reroute the water in a different direction. So at Smith and Morehouse, there was really nowhere to go because it was such a long embankment. It's almost 3,000 feet long, 4,000 feet long, right? So they built the dam in two segments, an east end and a west end, and they routed the water down the middle. So the first thing they did was they built their outlet works. And then they started the middle portion of the dam just high enough to where they thought they could get by with a year or two of runoff. And they allowed all the water to go out the new outlet works and then built the rest of the dam up before it. The last part that was filled in was the middle portion of the dam. There were some interesting things that went on during construction on that dam. I mean, it's 70 feet high, 80 feet high. Rock trucks, have you seen rock trucks at mines and on the roadways, road construction? So these things would come up the hill, you know, fairly steep. They'd get as much energy as they could, get up the hill, and then they couldn't make it. And they'd slam on their brakes. I've seen rock trucks that would start to tip backwards. And the drivers and the operators would slam on their brakes. They're 2 or 3 feet off the ground. They'd have to bring a dozer over, chain it up, and then pull it up the rest of the way. So it gets pretty intense on some of these projects. I almost got hit by a road grader one time. Well, no, I did get hit, but the guy that was standing next to me almost got hit. I had to kind of push him out of the way. So, anything else? Yeah, sorry.
What's curious behind supplementary education for when you start a business?
No, but that's what's great. Well, yes and no. When I was hired in St. George, I was hired by a national firm called Kleinfelder. They're a great firm. Worked for them for 5 years. I was managing their office. And they did a great job of training me on how to run a business. They were very good on, you know, this is what financials look like. So now I'm looking at accounting, you know, reports and things and what it means, what these numbers mean, where you're making money and things like that. So, but there are classes that you can take. I send all of my junior engineers, a lot of them, they're going to be staying with the company, to Leadership Institute at the American Council of Engineering Companies. And what they do is they talk to them about marketing, they talk to them about legislation, they go over financials, they go over all of these things that are business related and not engineering related, because they need to understand those things. How does the things that I do affect the company? What's interesting is we have a list of words that we do not use in any of our reports and documents. And do you know what those words are? They are words that can cause us legal issues. They're kind of fuzzy. They're not. So, for example, we don't use the word determine. We assess. And because there are legal definitions on what determine means. You know, so we avoid specific words whenever we're writing our documents. The one thing I did find is do everything you can on learning how to write. When we write reports, oftentimes we're writing reports for people that don't have a technical background. You know, so we're trying to convey to them recommendations on things that they need to be doing, and you need to try and simplify it. You don't have to give them the reasons why you're doing it, but you have to be able to tell them and explain to them why they need to do these things. So technical writing is very key and very important, at least it is in the geotechnical engineering side. Any questions? Yeah, we did. Right.
How does that, do you guys work on that?
No, we don't. I don't know if you're familiar with what's called the NEPA process, NEPA. It's the National Environmental Protection Assessment something Act.